Okay, so we went over this first example, and as we said, that's a determinant problem, right? So it's much easier if it's just determinant. Okay, so then we said for the determinant or indeterminate, either one. The most ideal case, if you can use superposition, use superposition. It's always easier. Right. Okay, so today let's go over a few more examples, more on the indeterminate beam. Okay. But before we start a new example, let's look at this example here. Okay, the one at the bottom here. Okay, so for this one, it's determinate or indeterminate? Anyone not sure it's determinate or indeterminate? Determinate or indeterminate? Determinate or indeterminate? I don't say a clear answer. Indeterminate, right? Okay, anyone disagree? It's indeterminate. Right? The quick judgment is, if you look at this beam, you can look at it. If you remove that restriction, that strain there, you actually have a cantilever beam, and that's determinate. Now you're adding another restriction, so it's becoming indeterminate. Right? Okay, so it's indeterminate. Now, how can we find out the deflection of this point? Let's say delta the point B for this indeterminate beam. You use the Fed.com. That's a general idea, right? So use the equation of equilibrium. You can write it about all these reactions, and then you don't have enough equation to solve it. Okay. So in this case, we can use superposition, right? So in the beam, actually the Fed.com is actually easier in a sense, because if you use a superposition, all the basic solutions you already have. So you don't have to use the deformation equation to find it, right? Remember the Fed.com. Okay, so the D part, the deformation. You write the deformation equation, and you find the deformation, right? That's basically the theory, the idea. But in this case, if you use superposition, the deformation will be given. So you can find from the table what is the solution there. Okay, now for this one, indeterminate. How do we approach it? How do you solve an indeterminate problem? Okay. First, you say it's indeterminate. You write it down equation, you find it. Second, you find the redundant restriction. You identify one. And there are multiple ones you can select. Right? In this case, for example, you can select the RA as redundant, or you can select the M there, or we call this MA as redundant. Or you can select this RC here as redundant. Okay, so based on this problem, which one you think will be easier if you select that one as a redundant? RC. Because once you select RC, it becomes a cantilever beam. And cantilever beam, we know the solution all given in the textbook, the table. Right? So therefore, the natural choice is select RC. You can solve it by select the other ones, but the other ones will be harder. The direct quick way will be just select RC. Okay, let's say we select RC. All right, so I have RC as a reaction. So RC, I know yet. So I have load P here. Now, what do we call this structure? What do we call this? The reduced structure. You reduce from an indeterminate to a determinate. So this one is a cantilever beam with two loads. So it's a determinate system, looks like a determinate system, and we call it, because it's not a real determinate system, because RC is not known. So therefore, we call it a reduced structure. So once you identify the reduced structure, next will be you just solve for the solution of this reduced structure. And now you can actually use superposition. All right. In other words, next will be you equivalent this one to, this will be two problems. You solve this one, right? How do you solve this one? Superposition, right? So you have one problem that is RC here, and then you have a second problem that is only P applied here. So this one plus this one will equal to the top one. Right? So you divide this problem into your superposition to multiple problems that you have basic solution already. Okay, now for each of these two now, we can always find a solution. Okay, so again, we need to use a table. All right, so let me just quickly show the table on the board. You can always just open your book. Right? Okay, so one skill you need is search the table, find your solution. Right? Okay, now this is the table we have here. Okay, so let's see if we can find the solution. All right. Any of this can be used as a solution? No, so we'll just move on. Next page. This one? Nothing? Nothing? What about here? Oh, it's fun. Okay. Maybe let's see what we have here. Okay, which one? The number? 4 and 5. That's what we're looking for, right? Okay, actually we did this last time for the determinant problem. Okay, now, because I want to do these two problems, so you can compare, say what's the difference between determinant and indeterminate. All right. Okay, so we have these two here. Now, which one would you like to use? They give you lots of equations here. Let me make it a little bit smaller so we can. Oh, wrong way. Okay, which one you want to use? This one, delta B, right? So the delta B is given here. Oh, here. All right, so let me just write it down. So the first one, you have delta B equals to 3EI PL to the third. Okay. All right, then this one give us delta B here. Delta B equals to 6EI PA squared, and then 3L minus 8. Okay, now we can go back to the screen. All right. Okay, what's next? Now I can use the table. I found these two solutions. What can we use then? Compatibility. Okay, so what's the compatibility in this case? Which part that moves very specially, right? When this moves this way, the RC will equal to the original problem. So this is the delta B from the load RC. This is the delta B from the load P. Okay, so what's the compatibility we can use? Okay, I heard RC minus P minus RA equals 0, right? Is that what you want to say? So that's the load here, RA, this way. Actually, RA should be RA, RC. This should be plus. The same direction. So that's the equation of equilibrium. And that two unknowns. Yes?
So you're saying that the bar does not bend?
Which bar?
The cantilever beam does
The
not
beam, of course, beam will bend, right? We talk about beam bending. So this beam will definitely bend. Okay, so what's the compatibility? What do you use here? That's the I heard some delta. So I heard something like delta B equal delta C. Delta C. Okay, what's delta C? What do you mean by delta C? First, what's the definition? Delta is this point, right? Okay. Delta at this point equal to what? Equals to this RC, right? The length of the cable, the E of the cable, the A of the cable. Because there, the C point going to move a distance that actually you have to stretch the cable. So how much the beam move at the point C has to equal to how much the cable elongate. That's the compatibility. So it has nothing to do with delta B actually, right? Because the delta B here, this point, this load will make this point move somewhere here, and this load will make it move here, and then the final will be this two add together. But you don't know the final. You don't know what it's supposed to be because this point is going to move. It won't be zero. So therefore, delta B don't give you that information about compatibility, and the part compatible is point C. That's the key. Okay, now can you find out delta C from the beam? How much this beam going to move at this point C? So how much this point going to move? How much this point going to move? Can you find it? Can you find the moment of this beam at this point C? Let's call this one delta C1. This one we call it delta C2. Okay, can you find delta C1, delta C2? That's my question. You all try homework already, right? So, okay, can you find delta C1, delta C2? That's my question. Yes. How? You have to use the equation. For example, for this one, now let's look at the book. Okay, for this one, for example, they give you Vx at anywhere. Now can you use this to find out the delta C? The displacement at the middle point. Yes, you just let x equals half L. Then you get that point. So we can find it. In other words, if you just use this delta B equation, it won't help you solve it. In this case, you have to use this one to find out the delta C. All right, so you found delta C from this one. Then you found delta C from this one as well. They give you the equation, right? Actually use this portion. Use the 0 to A portion. So you find delta C from here as well. Now this two delta C added together is how much the beam moves. And that movement should equal to this one. Equal to this, how much the bar moves. So the compatibility will be delta C1 plus delta C2 equal to the delta C of the bar or the cable. That's your compatibility. All right. Okay. Any questions now? Yes.
Which forces do we assume we already did? P or RC?
P is the load. So you know, I give you, let's say this is a 20 Newton. So the one unknown is RC. Okay. So because RC is unknown, that's why you need to use this relation. That's what we call compatibility. Once you have this equation, RC is in there, it's unknown. So you can use the equation to find out the RC. So this will be, this is equation 1. This gives you the equation 2, the additional equations you can use to find out RC. That's a general idea about the indeterminate problem. Because for determinate problem, you can always start from the F part, the free body diagram, equation of equilibrium. You can solve the equation of equilibrium, find all the load, and then you can determine the deformation. So it's done, one straightforward. But for indeterminate problem, you cannot go this way because there are too many unknowns. So you have to add another equation, compatibility, and then combine them together, solve all the equations together. That's the difference. Right? So that's the difference between determinate and the indeterminate problem. And for the beam here, basically the indeterminate part, the compatibility part, is become a displacement somewhere or angle at somewhere. So it's like more like a boundary condition, if you can call this point like the boundary, the boundary. So the boundary condition, actually the boundary can be any point. Or in other words, the compatibility can come from either the end point or can be from the middle, depending on the situation. Right? So in this problem, what you have actually is a beam here plus a cable here. So you basically combine the knowledge from chapter 2 and chapter 9, and that's what. Okay, any other questions about this example?
Yeah, if we wanted to find delta B, do we still use those B equations?
Okay, now the question is, what if I want to find the delta B? Can I find the delta B from here? Yes, because with this equation, I find out RC. Once I know RC, okay. So I know RC, then from RC, how much load? Let's say it's 5 Newton here. And then you can find out how much this point move. Use the table again, right? You can find the delta B. And then from here, this load here, you can find how much delta B. So you add them together. I mean, adding means sometimes can be subtract each other because it can be different directions. All right. Okay, any other questions? All right, another example I have actually is from the textbook. I will just show here. Actually, I can draw it here. Okay, so what I have is this problem. So we have two beams. One beam you can support a load, but sometimes you don't feel strong enough, right? And then you put another beam, basically support it. But once you put this additional beam here, now this structure is determinate or indeterminate? It's indeterminate. How many unknowns reaction do you have? You have RA, RB, RC, RD. So there are 4 unknowns, right? So 4 unknowns, how many equations do you have? You may have 2, or maybe add another dimension 3. So you don't have enough equations, right? Because you don't know how the load will be, how much this beam will deform, how much this beam will deform, or how much load will carry here. Let's say the ideal association. Okay, that's all symmetric. So RC. Okay, let me just draw on the screen. It's easier. Okay, so ideal association, if you have everything symmetric, so you're going to have, this will be point A. So you're going to have RA. And then this part is symmetric, so you same value. So RB will equal to RA, so you can say it's RA, right? That's equal to RB, or RB equal to RA. And then here you're going to have RC. And here you may have the same. Let's say it's RC, it's RD, but it can equal to symmetric. It's a simple case, right? But still you have 2 unknown. And that 2 unknown, actually you cannot tell how the load will distribute between the RA and the RC. There's no way you can use the equation of equilibrium to find it. You can write sigma Fy equals 0, right? So RA plus RC times 2. So the sigma Fy equals 0. You're going to have RA plus RC, and the 2 of them, 2 ends, so equals to the load Q times L. And that's it. That's one equation, 2 unknowns. So you cannot find it. That's why it's indeterminate. Actually, pretty easy because it's straightforward to judge it. Because this one, if you remove this beam here, what do you have? You have a simple beam, so it's determinate. Now you add one more restriction there, so it's indeterminate. That's how you can quickly judge it. All right. Okay, so it's indeterminate. That's one thing we'll agree on, right? Okay, now how can we solve this beam? Find out the load, the reactions, or say, for example, we want to find out how much this point is going to move, delta C. Don't call it C. I think delta O, middle point. Okay, reduce it. Find the reduced structure. Reduce the beam. Okay, how would you reduce it? You remove the redundant restriction, right? So what we can do is we can change this one to this problem. So I'll just draw it here. So you're going to have this beam, right? So the load still be distributed load here. But the other one, instead of this restriction, you actually put a reaction here. that we call it RO from the bottom beam. But this RO is unknown. Even though it's unknown, but we can treat it as a load. Okay, now with this RO, okay, what we can do then? Use superposition, you can solve it. Okay, so let's use superposition. So from the table, you can find out this will equal to this two problem. One is you have a distributed load, Q here. Another one is you have this situation. So you have a RO here, right? So basically these two add together is that problem. Now for each one of these two, can you find the solution? Yes, we can find it from the table, right? So the table you can get it. Okay, so which one are you going to use from the table? Okay, so here is the table. Oh, here, that's one situation look like that, right? Distribute load, so you can get the delta C. So from distribute load, you can find out the delta C. So delta C, C means the middle. So in our case, we call it delta O, right? So we can get one delta O. That's 5/384, right? Okay, what about the other one? We have this one here, right? Oh, this one here. So if the constant force, we have this 48. Okay, so let me just write back to here. So this one, the load, the delta O from the Q will equal to 384 5QL4. And then this will be delta O from the load RO will equal to what? Negative, yes. Someone remember it, right? Correctly. Negative, that's 48. So you have negative, that's RO L cubic 48 ER. All right. Now, what's next? What's the compatibility? That's the key part. I always want to go over the compatibility equation, and that's the most challenging part. Now, how can you find the compatibility? When you add them up, okay, so add them up, I got the delta O of the, let's say, top beam, right? That equals to delta O from the Q, then plus the delta O from the load RO. Okay, I add it up then. Does this equal to 0 or something? Well, equal to 0. Well, this point move 0. How many of you think this middle point is going to move 0? Okay, I got 2, at least 2 votes. All right. Now, why you think at this point we're going to move only 0? Is there a restriction there? Someone like a rigid holding there? No, there's no rigid restriction there. You have like a pin support there, right? Then you will move 0. In this case, it's not. Because this point, O, from the top beam here, from this top beam, it's attached to the bottom beam. So when the load is applied, it will push on the bottom beam. But the bottom beam is not rigid, so it's going to deform. So therefore, this point is going to move. So it won't be 0. Okay, but how much is this point move? The top beam, how much the top beam moves? And we know it's not 0. So don't come back to 0 again, right? We already deny it's 0. Okay, how much this point? Top beam moves at this point. Okay, how much the bottom beam moves? Same. That's the key. That's the top beam, bottom beam. They must be compatible. They must agree each other. They move the same distance. That's the compatibility. Okay, once you realize that, equation will be easy. Okay, what's the equation then? So the delta O from the top beam should equal to the delta O of the bottom beam. Right? Now, can we find the delta O of the bottom beam? Okay, let's draw the bottom beam. Okay, so bottom beam is here. Right? 2-point support. And then you have what apply on the bottom beam. You have one contact point from the top, and that is the RO. So it's under one constant force, RO. We don't know the value yet, but that's the RO we'll apply there. Okay, now for this one, can we find the solution? So what's the delta bottom? Can we find the solution? It's already there, right? So it's basically 48 E prime I prime. That's why I put a prime. Because the bottom beam may have different E, different I. That's why I say, okay, but the equation should be the same. So you have RO, and then L prime, and then cubic. Well, if we don't know the length of the beams, then we cannot solve it. So you have to know all the dimensions, then you can solve it. Right? Okay. Now, in everyone's mind, is the compatibility equation clear?
Can you write it?
Okay, can you write it? What's the compatibility equation? Okay, you help me write it. Let's say we use this space here, write it. Okay. What's the compatibility equation here? Fill in the blank. So the bottom beam, how much the bottom beam moves, should equal to how much the top beam moves at that point O. That's the compatibility, right? Okay, so let's just copy the equation then. How much the bottom beam moves will be RO L prime cubic 48 E prime I prime, right? Okay, how much the top beam moves at that point? You have 5 QL4 384 EI. Okay, so here I forgot to put the EI here, right? And then plus your RO L cubic E, oh no, not EI, 48 EI. That's a compatibility equation. Right? Okay, do you have everyone agree this is the compatibility equation? Yes, all right. Now can we find the RO from this equation? Can we find the RO from this equation? Yes, everything else is known. Q is known, E is known, I is known, E prime, I prime, L prime, they're all known. So you just calculate the R0 there. Okay, once you find the R0, now can you find out how much this point is going to move? What's the delta O? Yes, you put it back here into this equation. You get it, right? All right, any questions about this process? So we went through 2 indeterminate beam now. Okay. So after class, I'm for sure before Monday, try another indeterminate problem from the book, homework example or in other place. Just random pick one, see if you can solve it quickly. Yeah.
So the exam is still going to be this Monday.
The exam is coming Monday. That's as scheduled. We have the classroom will be the same. This classroom and the other classroom. All right. So remember, you just sitting next to an empty chair. Don't sit next to somebody. If everyone sit down quickly, we'll just start a few minutes early. Yeah.
Obviously, chapter 9, about 7, 8.
7, yes. 8, no. Okay. So we're going to have one more example about chapter 7. All right. So let's move on. Chapter 7. Okay. What's chapter 7? We talk about what? Plane stress. Plane strain. That's the concept, right? So we more focus on the plane stress. So we need to know what's a plane stress. And then for plane stress, the key thing is if you have a coordinate, let's say 1 point, you have sigma x, tau x, y, and sigma y. Okay. Then if you rotate the coordinate, okay, what's the stress in this any arbitrary theta direction? The sigma in this x prime And also, what's the tau here in this direction? You need to be able to calculate it. How do you calculate it? The formula there, right? It's on the formula sheet. So you need to understand the formula sheet. Don't ask me what's the theta there in the equation. You need to know the theta is how much you rotate. That's it. Right? Yeah, I do get people ask me what's this variable, what's the sigma stand for, what's the A stand for. So formula sheet just help you, remind you to you don't have to memorize the equation, but not to try to explain everything. You have to understand it. All right. Okay, so that's one key equation, rotated. But this thing, actually, we can also use more circle to find it instead of using equation. So a key scale will be drawing the Moore circle. Okay, now how to draw the Moore circle? We talk about two approaches. One is point A, point B. As a diameter, you get a Moore circle. Another is you find the center, radius, that's a circle. Right? Either way will be fine. But at least one thing you need to know is where is the point A. So this direction here, let's say I have this one, let's say 10. The shear stress is 5. You need to know this surface here, this surface, on your Moore circle, where this point is. Because that's the baseline. Right? We talk about principal direction. That direction is basically refer the angle from this baseline, the OA direction. So you need to know where this x-axis is on your Moore circle. And then you can talk about the theta, right? Okay, so that's a theory. I think we talked about it already. So let's use the example again to go over the process, right? I always like to use examples. I think it's easy. Okay, now let's say give an example. You guys come up with some numbers. We'll do some random number. Let's see what where this thing can turn up.
Sigma x.
Okay, let's say sigma x equals 10. All right. Sigma y 5. Okay. Tau xy 2. Okay. You'll try this.
Yeah.
Everything's positive, right? But the situation can be some are negative, some are positive. So later on you flip it. Just try all different cases. Yes.
What about when it could be like an angle? Like some example or some textbook one, it could be like an angle as well.
Can be an angle about what?
It just says like theta is like 35.
Yeah, so they give you a theta value. Ask you, okay, this is the stress in the x or y direction, right? Ask you if I rotate to 30-degree angle, what's the stress there, right? That you can use the equation, just plug in theta equals 30 degrees to calculate. That's one way. Second, we'll see from the Moore circle how to find it.
Well, it's theta 2, or it's like sine 2 theta.
Yeah, the equation is sine 2 theta, cosine 2 theta. Okay, let's draw this Moore circle. Then we say how you can use Moore circle to find out the stress in the 30-degree angle. Okay, so that will be it. All right, let's draw the Moore circle first. All right, so here is the plane. Remember, this is sigma. This will be the tau. It's point downward. That's the positive direction. Okay, so we need to set up scale. So let's say here is 10. Here is 5. And here is 2. So this will be 5. Okay, now let's draw the Moore circle. So this will be 5. 5. And then 10 will be here. 10 will be here. So it'll be 5, 10. Okay, draw the Moore circle. Let's say, where's point A? A is 10 and 2, right? Okay, 10 and 2. So this is 5. So 2 must be here. So this is point A. That's 10 and 2. Is that correct? Okay, now where's point B? 5, negative 2. Okay, 5 is here, negative 2. I must go up 2, so that's here. So this will be the point B. Now can I draw a Moore circle? Yes, I connect A and B. That's the diameter, right? Okay, with this diameter, draw the circle. So just draw it. So this will be the circle. Okay, so actually I'm a little bit off here. All right. Okay, now where's the center? Can you determine the center C? Okay, C equals to half the sigma x plus sigma y, right? So that's 10 plus 5 over 2, so 7.5. Well, but just reading the figure, should that center at 7.5? Yes, because the circle here, right? So that's a 10 and 5, they're must be in the middle, so that's 7.5. So it makes sense. So visually, if you draw it correctly, visually you should see the correct number. All right, so we have A and B and the center. Now we can answer all the questions. Let's say first, what's the principal stress, sigma 1? What's another principal stress? And what's the maximum tau? Okay, tau equals to 7.5, I heard. What's tau? How do you find the tau? Radius. Now can you find radius of this circle? Is it 7.5? Is it 2.5? No. Okay, can we find the radius? Okay, this is the radius, right? Okay, now you draw this triangle. Okay, so what's this length from this point to here? This length? 2.5. Okay, now what's this side? The other side? 2. Now can you find the radius? So 2 square plus 2.5 square. Anyone got a calculator?
3.2.
What's the value?
3.2.
3.2. Okay, so we got R equals to 3.2. Now, what's tau maximum? 3.2. Okay, now what's the sigma 1? Should that be 7.5 plus minus or plus? Plus. Sigma 1 is the maximum. Always you go left here. This point, that's a sigma 1. So it should be 7.5 plus 3.2 plus the R, right? Or you write the equation. So the sigma 1 will equal to the C plus the R. So that equals to what? 10.7. Okay, now what's sigma 2? 7.5 minus 3.2. Right? Okay, now what about the principal angle, theta P? Where is that angle on the graph? If you can draw it, you can find the value easily. Okay, where is the first principal direction? It's right here. This is the first principal direction, right? Where is your original x? It's here, along the CA. That's the original. Now, how much you have to rotate from your original x direction, go to the sigma 1 direction? It's this angle here, right? But that angle is 2 theta p. So therefore, your tangent to theta p should equal to 2 over what? 2.5. Okay, now can you find the theta p from here? Yeah, arctangent. Yeah.
Isn't it 2 times 2.5?
Yes. So the theta p here is theta p1 because the 1 go to the first principle. But if you know theta p1, can you get the theta p2?
Yes.
Yeah, just plus 90 degrees. All right.
Is it not 2 times tau? 2 times
Yeah, right?
Why 2 times?
One of them has it 2 times.
Yeah, but 2 times tau over what? Yeah, it's basically, let me just, okay, what we are doing is you look at this is the angle. So it should be this length, that's 2. And then over this distance. If you do the other way, 2 tau, then you should over, it's the same as, let me just draw it here. So you have this angle here. Okay, one way you get this angle is you get this length versus this length, right? Another way you can do is this whole length versus this twice this length. That's the same thing. Yeah, both you're doing here. This will be the angle, right? Give you the tangent. Or you can use this line, so I can draw a line here. Now you see what I mean? Yeah, the same thing. Yeah.
I have two possible theta p's. That's correct. First, I'll have.
Well, you find the theta 1. Let's say it's like look like 20 degree. Let's say. Okay. Now where is the sigma theta p2? You just keep going at the 90 degree.
That's how I thought first I had to get. It was going to be 2 theta p equals 1 plus 180 degrees.
Yes. Yes.
And then you just add each.
Yeah. So therefore, your theta p just add 90 degrees. Yeah. All right. So on this graph, it's actually showing this is theta p1, then the other one you go here. Actually, you go this one. So you just add 180 on the Moore circle. But that's 2 theta p, you add 180. All right? Okay, any other questions about the Moore circle? Yes?
So theta P1 is 19.32.
Yeah, 19 degrees. So I estimate 20. That's pretty good estimation. Okay, so 19 point, what do you say? 19.2, 0.3. Okay, yeah.
How do you, so theta P2 is plus 90?
Yes.
What does that represent?
So it'll be 19 degree plus 90. So you have what? 109 degree. So that's your theta p direction. Yeah.
So when I'm getting my second theta p, I need to be mindful whether my first theta p is negative or positive. However, I'm looking at the absolute value.
Yeah. So basically, you go 90 degree more or 90 degree less. Either way, it's the other direction.
But my answer will always be a positive value, so you put an absolute.
All right. Oh, hold on. Any other questions? Yeah. Yeah. Well, okay. What's the value for theta s? Actually, I have answered his question. What about the 30 degree? Okay. What's the stress at 30 degree? Where is the point for 30 degree? That's my question. On this Moore circle. It's already look messy there, but where is the 30 degree point direction? How do you find that 30 degree? So this is the CA, right? BCA. This is the line. That's your x direction. So you go up what? 60 degree. So you go up. Okay, let me just draw here. So this is your x direction. So you go up 60 degrees. So it'll be somewhere here. That's the 30 degree stress. Why 60? Because on the Moore circle, always 2 theta. So if you go 60 degree, the other stress there is actually on the physical plane, you rotate 30 degree. That's the reason. Because he asked for 30. Remember the guy back from you? He asked, so what's the stress at a 30 degree angle? That's why we say 30. Yeah.
That's correct. So anytime I get an answer for theta p, it's going to be going in a positive.
You can give a positive 90 or negative 90, it's the same thing. Yeah, I'll take it. Yes. All right. Yes. For the maximum shear, yes. You add from the sigma 1 direction. 45. So on this plane, actually here. On this plane, is actually you go 90 degree more. Because that's 2 theta.